Imagine, you are assigned to manage parcel deliveries in a busy neighborhood. Every day, you must cover dozens of streets to deliver packages and return to your warehouse. But how can we make the routes as efficient as possible?
Phase 3D, a residential area served by E-Prime, a Shopee warehouse responsible for delivering parcels across dozens of interconnected streets. So, the goal here was to develop an optimized delivery route strategy, one that covers every required streets while traveling the shortest possible distance.
This is where the Chinese postman problem, also known as route optimization problem, comes into play. Its purpose is to find the most efficient loop that passes through every street at least once.
Naturally, some roads may need to be repeated, but the challenge lies in minimizing those repetitions. That's where optimization techniques shine, figuring out exactly where and when to double back, so time, fuel, and effort aren't wasted.
Now, let's talk about how to solve this problem. The Chinese postman problem, also known as the route inspection problem, focuses on finding the shortest route that visits every edge of a graph at least once and return to the starting point. It's inspired by a real-world scenario where a postman needing to walk through every street in an area while minimizing repeated paths and total distance. Let's take a look at this graph as an example. The first step in solving the route optimization problem is to determine whether the graph is Eulerian or not. So, how do we know this? A graph is Eulerian if all its vertices have an even degree. If exactly two vertices have an odd degree, it's semi-Eulerian, meaning it has an Eulerian path but not a circuit. But if there are more than two vertices with odd degrees, then the graph is non-Eulerian, and that's the case here.
In this graph, we identified four odd-degree vertices: 1, 2, 3, and 5, which confirms that it's non-Eulerian. The next step is to pair these odd-degree vertices in a way that results in the least additional cost. There are three possible pairings, but the most optimal matching is 1, 3, and 2, 5, with a total added distance of 18 meters. Once we add these pairs, the graph becomes Eulerian, which allow us to construct an Eulerian circuit, also known as the Chinese postman tour. The optimized route is 0 to 3 to 1 to 3 to 4 to 6 to 5 to 2 to 5 to 4 to 2.
In our study, we applied this approach by modeling phase 3D as a graph. Each street represented an edge, and every intersection or delivery point was marketed as a vertex. The graph contained 44 odd-degree vertices and 21 even-degree vertices. We designated the E-prime warehouse as vertex 0, which served as a starting and ending point for the delivery route. Since many intersections had an odd number of connecting roads, a perfect loop was initially impossible. Using the route inspection algorithm, we identified and paired these odd-degree intersections. Then, Dijkstra algorithm calculated the shortest path between each pair to minimize additional distance. By duplicating only the necessary streets based on these calculations, we transformed the graph so that all vertices had even degrees, enabling the construction of an efficient Eulerian circuit. The final result was a complete delivery loop of just 16.6 kilometers with a backup route of 16.8 kilometers to accommodate potential traffic or delays, ensuring timely and cost-effective parcel delivery across Phase 3D.
So, you see how the Chinese postman problem really shines as a tool for optimizing delivery routes, especially in tightly connected areas like Phase 3D. By thinking of roads as a graph, CPP helps us find the shortest path that covers every street at least once, with as little repetition as possible.
In phase 3D, this meant cutting down the total travel distance. which directly improves delivery speed and saves on fuel costs. Of course, real delivery routes don't always go as planned. That's why we included alternative routes to keep things flexible and adaptable.
As e-commerce keeps growing, using Chinese postman problem and other mathematical tools will be key to building fast, reliable delivery services on a large scale.